All right, so today we want to reinforce the information that we've seen over the past few lectures. I've technically presented everything that you need to know about WebSockets, the handshake, and the frames. And for the next two lectures, I want to go through. Oh yeah, today is definitely juicy content. I want to do demos exploring all of this. So I have my Windows set up here to be able to go through first the handshake and then decoding frames, and then I'm going to jump over to. I want to resize that a little more. Then I want to jump over to some code and show you examples of doing bit manipulation in code. So we got some good demos. Going on today. So let's start with the handshake. And actually, I meant to ask this right before lecture, but anybody have a site? By default, I'll use Twitch, but a site that uses WebSockets. So we can grab a key. I want to go through this procedure. We want to grab the WebSocket key and generate this accept. I want to walk through this procedure. This slide is so important. This one slide is pretty much the entirety of Objective 1. So I want to go through this, not with code, but just make sure everybody understands exactly what this slide is saying. So anything other than Twitch, or do you just want to see Twitch? Doesn't matter what site we go to, other than what site we see on screen. Waiting. It's going to be Twitch. All right, so let's go to a site that uses... let's pause that. And somebody mentioned in another stream that during lecture that there are actually sleeping streams, and now Twitch is recommending sleeping streams. Two of these, I was looking at them before, like, what is Twitch recommending? This is under my bot account, and which is a fresh account. I haven't done anything on Twitch besides build the bot. And with a very fresh account with no history, Twitch is recommending sleeping streams to me. Like, is that really, that's not juicy content. That's the opposite of juicy content. Like, what the hell is going on there? But, and it's literally just people sleeping. Actually, I have to, no, I'm live now, so this will work. I was going to say, I might have to go to one just to get some WebSockets. I thought that was banned. So I thought that was banned on Twitch. That's what I thought. I thought that was Twitch's stance on sleeping streams. But apparently not. Apparently Twitch is pro sleeping streams, even to the point where it's recommending them to new users. Hey, welcome to Twitch. Watch people sleep. That's our hot content here. I don't know what kind of shift they had at Twitch to go from banning it to promoting it. But hey, they'll do what they do. So here we have our WebSocket connection. What I did was went to the network tab, sorted by status, and looked for a 101. This is my WebSocket connection. And maybe Twitch detected people sleeping through lecture. Thought that's what you wanted to see. Yeah, the bot saw that the people were sleeping watching the bot and wanted to recommend it to me. So I have the request. We can look at the messages to see the chat happening. And what we're interested right now in is this WebSocket key and accept. So to establish this connection, my browser sent this request, a request with these headers, a GET request, so this is the whole request, to the server, to Twitch's server, and this importantly had three specific headers. The connection upgrade header saying this is a request to upgrade this connection. The upgrade header saying I want to upgrade to a WebSocket connection. And the WebSocket key header, which is a very specific key, which is very important to the handshake. The other two say, hey, this is a WebSocket connection. In your homework, you're probably going to know that just from the URL. You're going to say, oh, this is a request for /socket or /WebSocket. What I put in the homework. So you're going to know that it's a WebSocket connection. You can get away with assuming that connection upgrade and upgrade WebSocket are there. But this WebSocket key, you need to read this to be able to generate the proper WebSocket accept. The proper WebSocket accept header. And then send the connection upgrade WebSocket and the accept. That's how we establish the handshake. If this accept is not exactly what it's supposed to be, you're not going to establish a WebSocket connection. So let's grab this key. And our goal is to use that key, take that key, and generate this. This is our goal, is to generate this exact string. So we should be able to walk through this procedure. And I recommend this as a way to get test cases. Just go to any site that uses sockets, grab a key, grab an accept, and that's a test case. On this input, your method or function that's going to generate these accepts needs to output this. So write a unit test and write your code until you can get your test passing. So if you haven't written a unit test since 1.16, which some of you unfortunately do, this is a prime example of a case where unit testing is going to save you a ton of time. If you are trying to debug this by writing your code, firing up your server, opening the browser, going to the 101, if it's even there, and then seeing if the connection was correct by going through the testing procedures in the homework document, that is going to take you a long ass time to develop. If you write a unit test, you write your code, you think it's right, and you run the unit test, and it tells you if it's right or wrong almost immediately, now you're cooking. Now you're getting a really good debug process as you write this method. Because there are, not too many steps here, but each step can be pretty tricky, can come with its own caveats and things that are going to trip you up. If you write this in one shot and it's right on the first time, I'd be thoroughly impressed. You can have my Jesse is Impressed award. So let's go through this procedure. We have the WebSocket key from the client. Now let's go to the next step. We're going to take this very specific unique ID, if I can get it exactly without the quotes. We're going to take this very specific ID. This is critical to the WebSocket protocol. If we go to the WebSocket RFC, we should be able to search for that ID, and we're going to see that exact string in the protocol. And this is, look, it took me exactly to where it's describing the handshake. This is how the handshake works. If you want to go to the source, go to the root documentation. There you go. And it has that exact string a couple of times in here. So we have that exact string. The next step. Is that weird that you don't mind eyeballing the raw hash? So these aren't, well, I'm going through the whole procedure anyway, but we haven't seen a hash quite yet. I guess kind of we have. I don't know. But the first step of the procedure is to take the key and append this GUID to the end of it. Now, these are both strings. This is actually a base 64 encoded string, but we can just treat it like a string for our purposes. We will have to worry about base 64 encoding towards the end here, right here. But this, we're just going to concatenate two strings. Hopefully I didn't lose anyone at that point. You're concatenating two strings. You read this from the headers. You take this very specific string, and you concatenate the two together, and you get this big old string. Everybody should be able to follow that so far. So now that we have this string, we have to compute the SHA-1 hash of this string. This is the first part where you will have to look through the documentation for your language and figure out how to compute SHA-1 hashes in your language. Please don't compute SHA-1 hashes on your own. Find whatever built-in way. I believe every major language has a built-in way to compute SHA-1 hashes. If not, you can pull in a library for it. I'm fine with that. We don't want to go through the minutia of how SHA-1 hashes are computed, but find a way to compute SHA-1 hash. A lot of languages, you just pull in a hasher. You give it the function SHA-1, usually as a string. You get a hasher, and then you use that to hash your string. For my demo, I'm not going to code for this because that's your job to. Let me clear these out. That's your job to go into the code and figure out how to do this in code. But I'm going to go through it manually. Clear all these. I was just making sure all these worked before lecture. So first we want to compute the SHA-1 hash. I'm just going to an online tool. I Googled, or DuckDuckGo'd rather, SHA-1 calculator and just click the first link. Easy peasy. Simple enough. I'm going to paste that big string and I'm going to calculate the SHA-1 hash. My SHA-1 hash is going to be this. And this is a hex value. Really, that's all we need to do is compute this SHA-1 hash. The problem is this is hex data. This is not a string. We actually need to be concerned about the bytes of this hash. And in your library, this is going to come back to you as a byte array. Now, this does not use any encoding. These bytes can be, whatever they're going to be. And in most cases, this is not going to be a valid UTF-8 encoded string. These bytes will not be able to be decoded using UTF-8. They won't be able to be decoded into a string. If you take this hash and print it out and try to, you're just going to get a bunch of encoding errors. Your program might even crash. If it's Python likes to just crash if it can't decode. Or you'll get just a bunch of garbage printed to the screen. This is not UTF-8 encoded. These are bytes. This is hex. So this is hex data. We can't do it. We just can't do it. But we need to send this back in a header. We need a header value containing these bytes. And as you all know by now, you can't put bytes in a header because the first thing you do when you get a request on your server is parse the headers as a string. And we have the assumption that we can parse those as ASCII text, because how else are we going to write our parsers? You know by now how hard it is to get the file from the body of a request that's in bytes, that's not a string, and extract that from the rest of the content and never converting it to a string. You know how difficult that is, and that would be impossible if we allow headers that are not ASCII encoded strings. And it is ASCII. You can't even have UTF-8 in the headers of an HTTP request. It has to be ASCII. So we can't put these bytes in a header unless we convert it to a string, and that's where base 64 is going to come in. Base 64 is going to take any array of bytes and convert it to an ASCII string. So I'm going to take these bytes. Let me make sure this is on my clipboard. I'm going to take these bytes and encode them as an ASCII string. And I won't get into the details of base 64, but it takes every chunk of bytes. Maybe I won't do it because I don't remember. I thought I remembered off the top of my head, at least the overview. It takes some number of bytes and converts them into a sequence of 7 bytes. But I forget the numbers though. But like for example, it'll take the first 3. Those aren't even bytes. Like it'll take the first 3 bytes. For example, I forget the exact numbers, but it'll take like the first 3 bytes and convert that into 2 bytes, where the most significant bit in each byte is always 0 to make sure that it's valid ASCII. That's how UTF-8, or that's how base 64 works. So I have a base 64 calculator here. I did the same thing. I searched for a base 64 encoder. A lot of base 64 encoders are going to take strings as inputs. We don't want that. We want a base 64 encoder that takes hex as its input. When you do this in your code, they should all take hex as the input, but a lot of the calculators online, I had to search a while. A lot of them didn't have hex. They were string converters, so I just added hex here and then clicked the first one. So we have our base 64 encoder, and guess what we're going to get is the output. Exactly what we're looking for. So I should have just done exactly what we're looking for. That is exactly the response that the browser is expecting, as long as you follow these steps appropriately. Append the GUI, the GUI'd, SHA-1 hash of the GUI, that's giving you bytes. Convert the bytes into a string using base 64, and then that's your accept. That's what you send back. Any questions on how to do that? Ascii, come on. Yeah, you can use the library for it. No questions on the handshake? Nope. Awesome. Thank you, Steven. Okay. Now, I want to do something similar. Let me shift gears here. Let me pull... Oops. Well, you just saw how to do the handshake in Scala. If you want to switch to Scala, you have Objective 1 done already. But let me run my web server here. Nope. Nope, that was over my... Never mind, it wasn't even on screen. And I want... Do I have the slides open still? Shoot. I gotta grab the slides quick. WebSocket frames. I want to get the format of a frame. You get the biggest image I have of it. Should be this one. And let's do the same thing with WebSocket frames and decode a frame manually. Just to make sure that everyone 100% understands what's going on, what you need to do in your assignment. So let's open my index.html. Sure. Jesse, hello. Fine. I never ran it. Okay, it'd help if my web server was running. Process finished. But why? That's why. Commented out. I was doing a 116 example. Oh, yeah, because this is the project that I just happen to have open. That's why. Okay, there we go. Listening on port 8001. Yeah, I don't go there. What am I even doing? Getting things confused. Localhost 8001. Jesse, hello. Submit. Content not found. Awesome. And then we go back to our server. And what I want to do is look at the WebSocket frame that was sent when I sent that message. So here's all my HTTP requests and responses. Cool. That's not the whole frame though. It's a request to close. Oh shoot. Give me 1 second here. Did I break my... break the handshake? I don't think so. Oh, because this one isn't using... I was using the wrong form. Silly me. Alright. I was using the wrong form. Okay. Now we got some web frames. Okay. So I want to make sure I have this one. This is the message. You know, here I'm decoding everything. And I have everything working properly, of course. But I shouldn't say of course when I just had that issue. But I was using the wrong form. So let's look at this structure and see if we can decode this manually and figure out what exactly is happening with this WebSocket frame. So you're going to get the frame in the same way that you get any of your HTTP requests. You're going to get the array of bytes or a byte string or whatever it is in your language in your library. What I'm doing here is converting that, not really converting anything, but I'm printing it out in this way so it fits the structure of the WebSocket frame a little better, just so I can visualize what's going on in this WebSocket frame. You're going to get it in the same format, and I highly, highly recommend doing this, printing out in this same way, or at least a similar way, so you can visualize the data that's being sent. It's going to help your debug process significantly, instead of just wondering why things are breaking and then waiting for an hour in office hours, then, you know, have myself or a TA say, hey, I'm not pawing through all your code and debugging this for you. You got to have a better testing procedure. Skip all of that, print this out, and then you can visualize and figure out what's going on exactly with this data and what's going right, what's going wrong. So let's pick this apart one at a time, one bit at a time, and we can start with this first byte, which we know is always going to be exactly this 1 0 0 0 0 0 0 6 zeros. I lost count 1, because the fin bit we're going to assume is always 1. The reserve bits are always going to be 0. And the opcode is always going to be 0001 to signify that this is a text message. Since we sent text from the browser, it's going to be text. If we sent a file, this opcode might be 2, because that's the opcode for binary data being sent. Ours is always going to be 1. If this is 1000, if you ever see that, that's a request to close the connection. That's the browser saying, I'm closing this connection. It means you did something wrong, something the browser didn't like, and it's closing that connection. So let's get rid of all of this, and we can say C. Let me paste this first. Nah, I don't need to paste that. So our fin bit is 1. Opcode 0001, or just 1. And our mask bit, we know is going to be 1. It's just, I'll stick with the thing down there. Our mask is 1. And then we get to our payload. I can already tell my payload is going to be less than 126. Because this 7 bits for the payload length is not either 126 or 127. Our payload length, let's stick with the documentation, payload len is going to be 0100110, which is going to be, I guess I can just cheat right here, 38. So I'm not sitting here converting binary in front of you. My payload length is going to be 38 bytes. That's how much information is being sent in this message. So that's the payload length. Since the payload length was not exactly 126 or exactly 127, I know that that's the entire payload length. I don't have these extended payload length bytes because the entire payload length fit in this 7 bits. So I know the next bit in the next 4 bytes in our case is going to be the masking bytes. These next 4 bytes are the mask. For our information, for what we're doing here. And then the data is going to start right here. We should have 38 bytes of actual payload. Before we get to decoding that, we'll finish decoding this, but I want to show just one quick thing. If I go back to the browser and I go to my chat, and spam my chat, we're going to see a WebSocket message where the payload length right here, we can tell it's 126. So in this case, the payload length is, the 7-bit payload length is 126. So I know that the next 2 bytes are my actual payload length. So those 2 bytes are going to specify my payload length. These 4 bytes are going to be the mask, and then all these bytes are my actual information that's being sent. Which you can tell, since it's 4 characters, spam, 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 all the way down, masked. And our payload length happened to be 956 bytes, greater than 125, so we couldn't fit it in these 7 bits. Actually, that'd be, well, let me stick with the one we already started. That'd be a nice example of doing this, masking. But here's the mask, and then we start reading our information. I like to do this 1 byte at a time. I know I like to say it as we read 4 bytes at a time and then mask. But in the code, when I actually code this up, I like reading 1 byte at a time and then figuring out what byte to mask it. So let's do it both ways. I'll start with 4 bytes. And first 4 bytes of payload, of masked payload. So here's our first 4 bytes of actual information. And let's get our mask back in here. And let's demask this. First 4 bytes of actual payload is going to be that I know it doesn't really matter, but I'll be consistent in my formatting. Is going to be a bitwise XOR of the mask and the payload that we've read. So let's XOR this. This is going to be 0 1 1 1 1 0 1 1 0 0 1 0 0 0 1 0. Now this is some good content here. Watching somebody manually XOR 2 8-bit values or 8-byte values. And this is our actual information that we read from that. This is the actual information that we read. That was being sent to us. And if we go to the browser again, I didn't pull one of these up. I don't have it queued up. So let's do a little searching. Binary to Ascii my binary value, convert, and we have our first 4 characters of our message. Since this is ASCII, these are all ASCII values. My first 4 bytes are going to be my first 4 characters. It just happens to be ASCII. If I typed in some Unicode, some non-ASCII characters in the chat, I'd have to find a different converter. I'd do binary to UTF-8. But these are our first 4 characters of our message. And if we look at this site, I believe I said just hi, right? If we look at the actual message that was sent, the message that was sent was started with username, like this. It was this JSON string. And when we decoded this, we got the open brace, the double quote, the U, and the S. That's what we decoded. So we could go through this entire payload, and we would be able to decode this entire string. So, of course, in your code, you would have a loop to do this. You would do this manually. I'm not going to do the whole message manually. But that's what your code needs to do, is demask the payload to be able to get to the original message that's being sent. Do that for all the bytes, and then you get the entire message. So let me explain what I mentioned before, that I like to do this 1 byte at a time. So I like to do, just for logistical reasons in the code, the big issue is like right here. If you're doing these 4 bytes at a time, what do you do with these last 2 bytes? You got to do something special there to avoid the index out of bounds. And I don't know, it can just be a little hairy. So if I iterate over these bytes 1 byte at a time, and then figure out which byte of the mask I have to XOR that with. So this byte, what I'm going to do is put this in an array and take the position of each value in that array, the index of that byte, take that mod 4, and that's the index of the mask that I need to use. So like if I have the 5th 0, 1, 2, 3, 4, the 5th byte, that's going to be at index 4. 4 mod 4 is going to give me 0. So I need the mask byte at index 0 from that 4 byte mask array. So I put the mask in an array, put your masked payload in an array, and then the position of that byte in the payload, mod 4, that's going to be the byte from the mask that you have to decode. Then you can iterate over all of these bytes, and just whatever the index is, mod 4, that's what you're masking, and then demask 1 byte at a time. Why mask instead of sending bytes directly? It's to avoid caching is the primary reason. This way, messages with high probability, 2 to the 6, oh my goodness, 2 to the 32, 1 over 2 to the 32 probability of having an identical message, assuming the user is sending messages of the same length. Actually, that'd have to be the same exact message. But if the user sends the same exact message, you have a very low probability of having the bytes be identical. So you're avoiding the server accidentally caching that and not processing it as a new message. So that's why every browser is going to mask their WebSocket messages to avoid the caching. Just in case a server gets some really aggressive caching and says, oh, I've seen this message before. Last time I received this message, this was the response, so here's the response. Which is nice when you're serving like HTML and CSS. We like caching. With WebSockets, not so much. We actually want to process every single message that's sent, even if a user is sending the same exact message multiple times. So masking makes sure that those messages are different each time. No caching. Any questions on this whole format? We just went through this whole format. Oops, my mouse is on the wrong screen. We just went through this whole format. Any questions on this? That's objective 2, by the way. Well, kind of. That's half of objective 2. No questions. Let's move on. Chat's pretty quiet this morning. We got low viewers too. I assume most of the class is working on homework 3 still. Which I get. I used to do that as a student. If I have a big homework due in a class, I'm probably not going to that class's lecture that day. I get it, but y'all better be watching this on YouTube after homework 3 is done. Nice. I like hearing that, cordless burrito. That this seemingly meaningless. Yeah, there's so much. It just looks like a blob of binary, but it has so much meaning. That actually says the username, whatever my randomly generated username was, said hi in the chat. It's just bytes. So you get to start seeing things from the perspective of a computer now, or a router or anything. This is all the computer sees, is these bits. This is what's sent over the wire, over the TCP connection. We, using our protocols, we assign meaning to all that. And then as long as the browser and the server are speaking the same protocol, WebSockets in this case, they're able to effectively communicate. Even though it's just ones and zeros flying over the wire, through the fiber, over the air, just ones and zeros, we make it have meaning through our protocols. If the payload length is 127, then there are, I wonder if I could do an example of that. I don't know, 64,000, 65,000. If this is 127, which we won't, by the way, we won't test on the homework. I said on the homework we won't send messages long enough to overflow your TCP buffers, which at the point where this would be 127, we'd be overflowing your TCP buffers. I'm not hitting you with buffering a second time. So I won't hit you with the 127 for payload length in this 7 bits. If this is 127, then the payload is the next 64 bits of the message. So the next 8 bytes will all be, like all of this that you see, would all be the payload length. If that were in that case. What's up, Johan? So payload length is either these 7 bits plus the next 2 bytes, or these 7 bits plus the next 8 bytes. Those are the three situations. All right, shifting gears again. I'm going to start with Python because that's the most popular. So in handling those masks, in handling those masks and the WebSocket frames more generally, you're going to have to do a lot of bitwise manipulation in your code. You're going to have to work with bits. So you have bytes. You already know how to work with bytes, but now we have to process those at the bit level. So let's just give a little bit of a coding tutorial because I don't think this shows up in any required courses on your way to 312. So let's talk a little bit about how to do bit manipulation in both Python and JavaScript. And then Monday's lecture, by the way, we're going to go into servers. We're going to go back to these Node and Python servers and see how to have multiple persistent connections and how to maintain references to those. That'll be all Monday stuff. We'll do more demos there. So in Python, we're going to have a byte string. This is how you're receiving your data. You have bytes that you're receiving over the TCP stream. So I'm just simulating receiving some bytes of information over the stream. And the first thing I'm going to do, let me run this one, Python 3 bitmask. Let me run this so you can see the output and follow along with the output. I think I want to do this side by side. No, wait, not what I wanted. Okay, I'm not going to do that. All right, Python 3 bitmask. I'm not just gonna. Let me try one more thing. Is it just a drag? No, not that. we're just not going to have them side by side. So the first thing I'm doing is iterating over the bytes of this information, and I'm printing out each byte in binary. If you want to see the binary in Python, bin, convert it to binary of the bytes, just like you would convert something to a string with str or an int with int. Binary, bin, convert this to binary. Then I'm going to print out the binary bits of each thing. And we get hello in Ascii, as we expect. Now note, this doesn't give you the leading zeros. If you want to format this a little more and get the leading zeros, you'll have to write a little bit more code, do some searching, figure out how to do that in Python. Like I did in Scala, I had to do some extra work to print out the leading zeros to make sure that they're printed out. So if you want to print out the WebSocket frames and have them nicely formatted, you'll have to. That's up to you. That's left as an exercise to the reader. Next, I'm going to create a mask. What I'm doing next is I just want to get the fourth least significant bit from each byte. So I'm going to iterate over the bytes again, but instead of just printing them out in binary, I'm going to print out a few different pieces of information. First, I'm going to print out just the binary like I have before, so you can tell which byte I'm working with. Then I'm going to mask that byte with this mask of 8 in this case. 8, if I just say mask equals 8, this is going to be an int. It's going to be the int 1000. So ints are always represented in binary in the computers, something we usually don't have to think about, but now we can use that to our advantage and understand, oh, if I have the int 8, that's going to be 1000. And if I take that int, that mask, as we say, and bitwise and it with my byte, I can extract a single bit of information out of that byte. So here we have this as our byte, the H in hello, and we're going to mask that with 1000. So that's going to zero out all of the bits except for the bit in this position, in this fourth position. So when I AND those together, I'm going to get just that bit, and it's going to end up being the number 8, and in binary, 1000. So if I need a specific value from a byte, like say you want just the mask bit, or you just want the 7 bits, you just want the 7 bits of the payload length, what you can do is create a mask that's going to be 7 ones, figure out what that is in decimal, create an int with that value, which will be 127, right? Create a mask with that value with 7 ones, but the 8th bit being a 0, the most significant bit being a 0, and then AND it with that byte from the WebSocket frame. That's going to zero out the mask bit and then give you just the 7 bits for the payload length. And we can see this with the other characters of hello. The bit that we're masking is a 0, so we just get 0. The bit that we're masking is a 1, so we get 8. The bit we're masking is a 1, we get 8. Bit we're masking is a 1, we get 8. So we have a value in binary that has 1s for just the bits that we're concerned with, and then we can mask out those bits. Like if I change this to 7, and this is, let me put the whole byte up there. Now I'm masking out the 3 least significant bits. There's 0, so this is 0. 101, that's going to be 5. 100, that's 4. And I'm just getting the bits that I'm concerned about, just the bits that my mask has 1s for. The scrolling jumps a little bit here. And we can do this on a per byte basis as well. So here I'm just taking the first byte. I'm accessing one specific byte of the array. For example, this would be 1. If I'm 1 and 7, no, it wouldn't be 7. I'm thinking backwards there. But we can extract a specific byte and then mask it with whatever we're looking for at that particular time, and then get that information, which is just 00 for this byte, unfortunately, and get that information that we want. We also have to send frames, so we are going to have to assemble WebSocket frames as well. And sometimes you have some information that's going to be in the higher order bits. Like, for example, if I want the left half of my byte, the most significant bits, to be 1010, and I want the least significant bits of my byte to be 0101, and I have my values for each of those. What I can do is use a bit shift. I can take this most significant bits and shift them to the left by 4 positions, and then add that to the least significant bits without shifting those, and that's going to give me my entire byte. And when we print that out, we get our 10100101, which is very useful when you're assembling these frames that you're going to send back to the user. You have certain bits that you need to set, and they might be higher order bits. Shift them, set them. Maybe you have a bit that you need to be a 1. Just take the int 1 and then shift it to the left as many times as you need. And what this does, this is going to take these bits and shift them to the right 4. This is effectively adding 4 zeros at the end. And then we add this bitwise and we're going to get what we need. You can also shift to the right. So say you mask a particular bit, and that's one of the higher order bits. You can shift to the right and remove zeros, which I'm sure you've done in 191 at least. Say I wanted to shift, I'm only interested in this bit. I can shift to the right 3 and then check if the value is 1. That means that bit was set to 1. Instead of always remembering exactly what that bit is, is this bit equal to 8? That'll work too, but you can shift to the right as well. Let's see the same thing in JavaScript quickly. So node, oh my goodness, bitmass.js. Let's do the same thing in Node. I have my bits, or my bytes from my message. This is how you're going to get your messages. Those of you using Node, you've used this buffer.from when you're sending your HTTP responses. I have my bytes. I'm going to iterate over them and print them in binary. In JavaScript, this is call toString, and then toString takes the radix, the base of the. I'm losing my words there, but you know what I mean. 2 is going to be binary. 8 would be hex. So we're going to print those out in binary, and same thing. The most significant bits, the leading zeros, are going to be removed. So if you want to format this differently, add your extra zeros in there or search on how to do that. There are plenty of solutions out there. I'm going to have a mask bit, same mask bit. Go through the same code. It's still ampersand. That's pretty standard in most languages. Ampersand is going to be a bitwise and. I'm going to print the original value. I'm going to print that value in binary. I'm going to print the masked bits. We're masking with 1000, so we get only this bit, which is 1 for this case, so we get 8 and 100, and then printing that in binary as well. For the next byte, that bit is 0, so I get 00 here. That bit is 1, so I get 8. That byte is 1, so I get 8. Bit is 1, so I get 8. So this is how we're extracting particular bytes that we want, and we can do the same thing. 3, 4, 5, 1, 2, 3. We can do the same thing we did in Python. Change that to 7. Now our mask is different, and we're masking the 3 least significant bits here. We're going to mask these 3 bits. And say we want to know. Well, let me save that. When we're low. We're already out of time. Let me just quickly go over the rest of this. And same thing here. We're going to AND a particular byte from the array, from the message we receive. Get a particular byte and AND it with a particular mask to get whatever bits we're looking for. And then same thing. The syntax here is pretty identical. The Bitwise shifting operators are pretty much the same. I think in any language I've seen, I believe I haven't seen them any differently than two greater than signs or two less than signs to to indicate a bitwise shift operation. So this is saying shift this byte to the right or to the left by 4 bits, and then add it to the least significant bits, and then we get our entire byte 10100101.